Hello everyone and thank you for being here. My name is Sandhya and my teammate name is Antonio Kioko. This presentation is on predicting medical insurance costs. Today we are excited to walk you through our journey exploring what factor truly insurance premium using data science and machine learning. Medical insurance is one of the most significant recurring expenses for individuals and families. With costs continuing to rise, there is a growing need to understand how premiums are determined. Our central question was, we can accurately predict a person's annual insurance charges using basic demographic and health related information. By answering this, we hope to support fairer pricing model and give consumer insight into what really affect their premiums. We used a dataset from Kaggle containing 1,338 individual records. The dataset is clean, no missing values, and includes key features such as age, sex, BMI, number of children, smoking status, reason, and the total medical charges incurred. These features reflect both demographic and lifestyle factors that ensures typically we use when calculating premiums. The structure one of the dataset made it suitable for building predictive models. Before building any models, we cleaned and prepared the data. First, we removed outliers in the numerical columns like charges and BMI using the interquartile range method. These outliers could distort model performance if left unchecked. Next, we encoded categorical variables like smoker status, sex, and reason into numerical form so that machine learning models could use them. These pre-processing steps helped ensure accurate and reliable predictions. We begin our analysis by exploring the data visually. This helped us identify pattern and relationships among the variables. We found that smoking and age were strongly associated with higher insurance charges. For example, smokers paid significantly more than non-smokers. We also noted a positive correlation between age and cost. In older individuals tend to have higher charges. Other features like reason or number of children showed weak or no correlations. This box plot shows how much of an impact smoking has on insurance charges. The median cost for a smoker is significantly higher and the range of charges is much wider. This suggests not only the smokers pay more on average, but that their costs are also more variable. This data visually confirms that smoking is one of the most important predictors in the datasets. The scatter plot visualizes the relationship between age and charges with color coding for smoker status. As people age, their medical costs tend to increase. What's striking is how the charges spike for a smoker across all age groups, especially among older individuals. This graph reinforces that age and smoking interact to increase overall risk and cost. This correlation heat map quantifies the relationship between numeric features. The strongest correlation is between smoker status and charges, approximately zero point 0.6, which is considered a strong positive correlation. Age comes next at 0.45. So, surprisingly, features like reason, sex, and number of children have very little correlation with charges, indicating they have minimal predictive values in our model. Now, from here, my teammate Antonio will explain rest of the presentation. Thank you.
To determine the most effective way to predict insurance charges, we tested three regression models: linear regression, random forest, and gradient boosting. Linear regression provided a simple and easy to interpret baseline, but it struggled with comparing non-linear relationships in the data. Random forest performed better. It captured more complex interactions and minimized overfitting by combining multiple decision trees. Gradient boosting, however, its own mistakes in successful steps, and with proper tuning, it delivered the most accurate prediction. We used 80-20 training test split and evaluated each model's performance using two key metrics: mean squared error, MSE, and R squared. Mean squared error measures how far off the predictions are, while R squared shows how much of the variation in charges that the model explains. When comparing the models, Linear regression initially looked promising, but this was before we removed outliers. Once we cleaned the data, its performance dropped significantly. In contrast, gradient boosting remained strong and became the clear winner. It achieved an R squared rating of 0.557, meaning it explained approximately 56% of the variation in medical insurance charges, and it had the lowest mean squared error. This model handled non-linear relationships like the interactions between age and smoking status much more effectively than the others. Our findings revealed three key insights. First, smoking and age emerged as the most powerful predictors of insurance cost. These two variables had the strongest influence across all models. Second, gradient boosting consistently outperformed the others due to its ability to capture real-world complexity in the data. And third, we learned that even with the modest data set, we could develop predictive tools that provide meaningful insight and practical values for both individuals and insurance providers. From a business perspective, this model offers several real-world applications. From an insurer perspective, we can use it to support dynamic pricing strategies, tailoring premiums more precisely based on individual risk factors. It also has potential in wellness initiatives. For example, by showing the financial benefits of quitting smoking, insurers can encourage healthy behaviors. From a consumer perspective, on the other hand, we can gain a better understanding of what influences their premiums. With this knowledge, they can take actionable steps like improving lifestyle behaviors or habits to potentially reduce their insurance cost. In summary, we successfully built a predictive model that estimates medical insurance charges using basic demographic and health data. Our best model, the gradient boosting, achieved stronger results with R squared value of 0.557. This project shows that predictive analytics can make insurance pricing not only more accurate, but also more transparent and fair. Looking ahead, we see several promising ways to build on this. First, scaling up with large and more diverse dataset could enhance the model accuracy and generalizability. Second, adding richer features like medical history, prescription, or lifestyle trends could lead to even more personalized predictions. Third, integrating explainable AI will help users understand how each input affects their premiums, build trust in the system. And finally, deploying this model with an actual insurance product or pricing could deliver real world impact for both insurers and customers. Thank you for your time.